Hello everyone. So we have discussed about plastic deformation mechanisms under shock wave propagation. So today we will discuss about shear bands, so which is a failure mechanism, or rather we should call is a precursor to failure, because the failure mechanisms actually eventually lead to crack formation, and that will actually fail the material. So we can call it as a failure mechanism, or better probably we will call shear band, we will call shear bands as a precursor to failure, or actually we can call precursor to fracture. So the complete failure may not happen when the shear bands form, but it will eventually lead to fracture. So what we will see now is some applications. So we will first start with some military applications, armor, or basically armor application, military applications. Military applications. Here we can see a projectile hitting a target. So this is the projectile and this is the target. Here it is, projectile. So after some time this the shear band will form. So these are the shear band in these areas. So it's called shear bands. So we are not going to discuss the basics of shear bands, because we already discussed in the introduction chapters, probably the first or the second lecture. So we have discussed about shear bands. So shear bands is basically severe shear strain localization zone, shear strain localization regions. So now here these portions, as I have shown, these portions will form a shear band, and that will help to form a plug. So this is called the plug, and eventually the plug will go out. So this is called plugging. That failure is called plugging, and this is plug formation, and that happens due to these shear bands. So shear bands help to form the plug, or the plug will go out of that target, forming a that is penetration, complete penetration by the projectile. And another case, this case, the diagram may not be very correct, but what happens is the target, this is the target is already deformed by the projectile. So this is the projectile, and so this projectile will move in the velocity of this way, and then there will be shear band will form the front of the projectile. So these will form a shear band, and so these shear bands, what will happen is, so we will draw this as shear bands. So these shear bands will eventually lead to shear cracks, and these cracks will lead to fragmentation of the projectile, fragmentation. So these fragmented parts will probably move out from there. So in the third case, which is also have a defense application, so this is an explosive is inside this metal casing. This is high explosive. So this is a metal cylinder. So what is happening here is it is with detonation, this I mean due to explosion or by explosion, this fragmentation happens. So just the metal casing is fragmented, made into lead to fragmentation with the help of explosive. So rather I should write explosion here, or it's a other way, you have the detonation which lead to explosion. So here you can see that this is exploding, and you can see that many fragments, and that is these fragments, if you can see the size and distribution of these fragments, distribution depends on shear bend formation. So basically what happens is, first the shear bend will form here, not exactly here, sorry, this area has a high explosive, right, this is a high explosive. So after the explosion, what will happen, the shear bends will form in this metal casing or the cylinder. So these shear bends, shear bend formation will decide, so what is the level of shear bend formation, that will decide the size and distribution of the fragments. I just want to let you know that there are several micrographs, that means microscopic images, in the Mark Meier's book, so that textbook. So you are requested to read that, I mean at least study that part of those micrographs, microscope images. So we could not include it in the slides. So if you can see this, you can study by yourself of those micrographs, that will be good for understanding the shear bends. So here we have only are showing the schematic diagrams, but here what we will discuss are different kind of applications, and this is manufacturing applications. Earlier we discussed about defense or military applications. This is the forging, you can see that this material will be forged here, this is the material, let us say some metallic material. So these is the shear bend. So shear bend formation shapes is generally is like that for for this kind of forging. And then there is another example of rolling. So these are the rollers, you can see these are the rollers, this is the workpiece, and then after rolling it will come out to be thinner sheets. So sheets or plates. So there are some shear bend formation here, you can see these are shear bends, and then these shear bends influence the final properties. Properties of the sheets or plates, rolled, I should write rolled plates. So the most important part is the shear bends are important here as well. And then another application which is also, these two applications are also manufacturing applications. Here we have the metal workpiece, also this is the metal workpiece, this portion is the metal workpiece, and then this is the cutting tool. So what happen is, you know that, I mean, you have, I'm sure that you studied in your manufacturing classes. For those for those students who are in mechanical engineering background, who have mechanical engineering background. So you can see that these are chip formation. I mean, even if you are not from mechanical engineering background, you know probably about that when you cut a metallic material with a cutting tool. So what will happen, there will be some chip formation like this. There are different chips. This is one chip, this is one chip. So there are like 4 chips we are drawing here. So these that region between 2 chips. So this is basically the shear bands. So that means the shear bands will form first, and that will convert the material to many chips. And this is very important because this chip formation helps to enable a higher machining rate. So that means shear bends ultimately helps to have a higher machining rate. And the last one, which is also one manufacturing application, punching and shearing. So this is the material, due to this punching, so it will have a shape like this. So where the shear bend will form here, so this is the place where the shear bend will form, in this line. So there are small shear bends here. So these shear bends will help, these shear bends will help smooth cut. So that means the shear bends are important. They are sometimes desired especially for manufacturing processes, but otherwise if you see for armor applications, so shear bends may not be desired in all cases. So we have already discussed about the basics of shear bend even earlier. So what are the favoring factors and opposing factors for shear bends? So first one is the thermal softening. That is favoring factors. When you are shearing material, so and as we can see that we have a shear bend is a very small thin band that is in the micrometer level, maybe tens of micrometers. So what happen is there will be a lot of heat generation, and then there will be very less time to dissipate this heat or conduction to happen to the outside area. So that is why the temperature generated will be very high in this region. So these heat, whatever I am drawing with the arrows, that heat dissipation or heat conduction from that region to the outside region will be difficult, and that is why a high temperature generation will lead to a softening of the material, that is called thermal softening. And what is the opposing factor? Opposing factors is the strain hardening, or we call work hardening. What is that? So that you already know that probably for metallic materials what happens, dislocation density increases with strain, and that will in return so harden the material. So so that is called strain hardening. So what will happen is the strain hardening will oppose the shear bend formation, and the thermal softening will favor it. And apart from that, we have even strain rate hardening. One is strain hardening and one is strain rate hardening. That means if you increase the strain rate, the hardening will also increase. And another favoring factors apart from this thermal softening is symmetrical softening. Symmetrical softening is actually result of this lattice rotation. So we talked about it, that lattice rotation are the rotation of the grains. When we are deforming the material, the grains will rotate and to change the orientation so that it can make the dislocation slip easier, to facilitate the dislocation slip. So the grain will rotate, and that will result the resulting phenomena is called geometrical softening. And as we have discussed here, the temperature rise will be high, and then temperature will not be able to go out of this region because of the less time. So that is why it is called adiabatic shear band. So the adiabatic, so we generally consider that no heat is go out of the band area. So and these bands are as I told, it is very thin, it is in the micrometer level, maybe probably tens of micrometers. You can see the real micrographs, the real pictures, actually micrographs from different microscopes. So that will tell you the exact thickness of the bands. So it depends on different materials, it depends on the loading, the how thick the band will be, and sometimes band may not be clear. So that you should just take a note of that. So not always bands not always clear bands. That means it may not take a shape of band, but severe shear strain localization, localized regions can be seen. So bands means it is a thin strip. So that may not happen in some cases, but still, I mean, basically it depends on the material as well. So if you see in the figures in the micrographs of the in the book, it will be it will make you clear about that. What I am saying, that shear bend is also a shear strain localization, but if it is in a shape of a band or long strip, I mean thin strip, that's then we call it as a shear band, but otherwise it is not, it is just a general shear strain localization. We will see in this case, so we have x, y, in this material is deformed in shear, let us say the shear stress is tau, and it is kind of a homogeneous shearing, it is not inhomogeneous, but what will happen is some part will be, we should have drawn this a little thinner. So this shear band, this portion is a shear band, but this will be a little thinner, we have made it a little thicker one. So due to these shear stresses, so this region is shear band. Okay. So now what happen is, this shows on the horizontal axis it has shear strain and temperature, they will vary in a similar fashion, and this is y axis. So let us assume that we are talking about this, and in this shear band region you can see at different strains actually we are talking about. Let us say sigma gamma 1, gamma 2, gamma 3, gamma 4, and then gamma C, that is the critical shear strain, and then at different gamma, let us say gamma 6, 7, so different values of gamma. So what happens is at that point sorry, we had a mistake here in the diagram. So what the diagram below it has a little mistake. So I'll just I'll just draw the correct one, and then so we can probably ignore this. And then please check the this plot like this. So what is happening in this figure? So after a critical gamma, so this will have a, you can see that the localized zone. So gamma will be more in this region. So that means when we increase the tau in this direction. So after a critical gamma, that means I would write critical shear strain, and before this area whatever strain we are talking is, this is homogeneous strain, and after that it was inhomogeneous because the shear band started forming. And then this, the last figure is, this is stress strain diagram, shear stress versus shear strain, and you can see that why I told it is a little incorrect, because the maximum stress tau max should be at gamma C, that should correspond to the gamma C. So that we had made a mistake. So while drawing it, so now gamma maximum is at tau maximum should be at the gamma C. So if you see this, that means at gamma C the shear band starts forming, and you can this is actually analogous to our necking formation at uniaxial stress strain curve, tension, uniaxial tension. So as you can see from a uniaxial tension test, so this maximum point, maximum load point will represent that after this point the necking will happen, neck formation. But in this case this is different, this is shear band formation. So what is the exact difference? Because in neck formation that is not at high strain rate. So we talked about localized deformation. Yes, both are localized deformation, both necking and shear band formation are localized deformation, but necking does not involve any high temperature or thermal softening. So in this case shear band formation we have a very high strain rate, and that will lead to high heat generation or temperature, and that is why thermal softening is there. That is why it is more severe than a necking formation, and shear band is very thin, severe localized region. We want to inform you one more aspect of these shear bands. So what happens, suppose if you have a material and shearing, and then this shear band is forming here, so there can be some void formation. So void, these are some voids, that is we call micro voids, that you know what is micro voids. This is not crystallographic voids, the small region, I mean these are without any material, but crystallographic voids are, they are in the angstrom level, and that is the gap between the atoms. So what will happen, the first the void will form, these are the shear band region. So these void will grow and they will join each other. That is called, as you know, void coalescence. So then this will lead to the crack. That means you see that this is now continuous and these forms the cracks. So this will lead to cracks, and these voids are generated, produced by tension due to, also tried, produced by tension due to residual stresses or tensile reflections. That you know what is tensile reflections, the wave reflections we are talking about, and we should understand that the flow stress of the material, that means the flow stress means the stress at which the material will deform plastically. So the flow stress in the band, that means shear band region, will be lower, or rather we should say would be much lower than the surrounding material. So void diameter of the voids are very close to the thickness of these the bands. That means in the order of, as I told you, maybe tens of micrometers. You can see in the book the real micrographs from microscopes, electron microscope. So I think that's all for today. So what we have discussed is the introduction to shear bands. So very basics of the shear bands we discussed in the initial chapters, initial lecture actually, and then in today's lecture we have discussed that how the shear bands influence our applications, like manufacturing applications. The shear bands are beneficial, and for military applications how the shear bands affect. And then we have seen that how these voids generation and growth and coalescence happens in the these shear band region. So you should understand that the voids are mostly concentrated on these shear band regions, so not the other region of the material. So these voids can lead to cracks and fail the material. So that's why as we have started this discussion, today's discussion, that shear band is a precursor to a fracture. So shear band itself can be a failure, but surely it is a precursor to fracture or failure. Thank you.